In this video, we're going to go a little more deeply into the uncertainty principle. We'll start by talking about the generalized uncertainty principle. Then we'll talk about the position momentum uncertainty, minimum uncertainty, and finally the so-called energy time uncertainty. So, for any two observables A and B, we can write that the sigma sub A squared, which is the variance of A, is just the inner product of the A operator minus the A expectation value applied to psi, inner product with itself. If we now call this entire quantity F, we can just write this as F inner product with F. Similarly, we can write the sigma sub B squared is equal to inner product of G with itself, where G is just B operator minus B expectation value applied to psi. If you recall the Schwarz inequality, it stated that if we take this sigma A squared times sigma B squared, is just the product of the two inner products of F and G, this must be greater than or equal to the inner product of F and G, F with G, modulus squared. So let's recall, before we keep going with this is where we stop now. Let's recall that for any complex number z, the modulus of z squared is equal to the real part of z squared plus the imaginary part of z squared, and this must be always greater than or equal to the imaginary part of z squared, because if the real part is 0, then it's equal, and if the real part is non-zero, then you'll always have this bigger than the imaginary part of z squared. But the imaginary part of z quantity squared is really simple to write down. It's just z minus the complex conjugate of z, and so you get 2i times the imaginary part of z divided by 2i quantity squared. And so that's just the complex part squared, the imaginary part squared, pardon me. If we take z to be the inner product of F with G, that's an arbitrary complex number, we can then write that the modulus squared of this quantity must be greater than or equal to its imaginary part squared, but its imaginary part squared is simply 1 over 2i times the inner product of F and G and its complex minus its complex conjugate, which is the inner product of G and F, quantity squared. So if we believe this, right, once we have this, we can expand each term of the expression. The inner product of F with G is just operator A minus expectation value of A applied to psi, inner product with operator B minus expectation value B applied to psi. This gives us, if we now bring A over to the right side, since this is Hermitian and this is just a constant, we can then write this as the inner product of psi with A minus expectation value of A times B minus expectation value of B applied to psi. So since A is an observable and therefore it's Hermitian, we can then expand. Since A is observable and Hermitian, we can bring it over like that. Now, we can then expand this by just multiplying it out and making sure we preserve the orientation. That is, we have inner product of psi with the quantity AB minus A expectation value of B minus B expectation value of A plus the expectation value of A expectation value of B, all applied to psi. This gives us 4 inner products. The first one is the inner product of psi with AB applied to psi. Then minus the expectation value of B times psi inner product with A psi. Then you have minus the expectation value of A times the inner product of psi with B psi. And then you have plus expectation value of A times the expectation value of B times the inner product of psi with itself. Clearly this is 1. So this first term is just the expectation value of AB. The second term is just the expectation value of B times the expectation value of A. The next term is the expectation value of A times the expectation value of B. And the third term is also the expectation value of A times the expectation value of B. So these two terms will cancel, and we get the expectation value of AB minus the expectation value of B times the expectation value of A. And this is all equal to F, the inner product of F with G. Similarly, if we do the inner product of G with F, we get the expectation value of BA minus the expectation value of A times the expectation value of B. Now, if you look up here at this product of the two variances, then you have exactly this. You have F, inner product of F and G, minus the inner product of G and F, all quantities squared. Well, when you do that, you can see that the two second terms are going to cancel because they're just constants. But the first terms are not going to cancel because there's an order to this. AB is not the same as BA. So we can now construct this equation at the top by saying FG minus inner product of FG minus the inner product of GF is just the inner product of AB minus the inner product of BA. But that's just the inner product of the commutator of A and B, right? Because it's just AB minus BA. And now we can replace up here this whole quantity with the commutator of the inner product of the commutator, sorry. So it becomes 1 over 2i times the inner product of the commutator of A and B, quantity squared. So the Heisenberg uncertainty principle is just the square root of this, right? Because this is squared, this is squared, this is squared. Everything's going to be the square root. This is the generalized uncertainty principle. And we can now apply this to position and momentum. So remember, the generalized uncertainty principle states that sigma A squared times sigma B squared is greater than or equal to 1 over 2i times the inner product of the commutator of A and B, all quantities squared. Well, if A is equal to x and B is equal to p, which is h bar over I d by dx, then we know what the commutator of these two operators is. It's just IH bar. xp is equal to IH bar. Sigma sub x squared times sigma sub p squared then is greater than or equal to 1 over 2i times IH bar, quantity squared. Well, you can see the i's cancel, and we get h bar over 2 quantity squared. And this is just a restatement of the Heisenberg uncertainty principle. If we take the square root, we find that sigma x sigma p is greater than or equal to h bar over 2. So this leads us to a notion that the uncertainty principle is not specific to the position and momentum, but it's general. Every two observables which do not commute have an uncertainty principle underlying what you can measure of them. That is, their variances or their sigmas. These are called incompatible observables. So two observables which do not commute are called incompatible observables. We'll come up and we'll see more of them as we move on into three-dimensional quantum mechanics. Incompatible observables cannot have a complete set of common eigenfunctions. That's a postulate. But compatible observables can have a common set of eigenfunctions. And this becomes very important later on as we talk about compatible observables. We can always find a common set of eigenfunctions. And that's really important later on. So the minimum uncertainty is h bar over 2, because sigma x sigma p is greater than or equal to h bar over 2. So the question is, when does minimum uncertainty exist? Well, minimum uncertainty shows up for x and p. We saw that in a harmonic oscillator and for a Gaussian wave packet. We can see that by realizing that in the derivation that we had before, we applied two inequalities. The first was the Schwarz inequality, which was that the modulus squared of f times the modulus squared of g is greater than or equal to the modulus squared of the inner product of f and g. And the second one was the magnitude of the complex quantity. If you recall, the modulus of z squared is greater than or equal to the imaginary part of z quantity squared, where z is equal to now the inner product of f and g. So when does the Schwarz inequality become an equality? Well, when the two functions f and g are multiples of each other, and so that g of x is equal to c times f of x, and c is a complex number. The second one becomes an equality when z is purely imaginary, right? So if z is only imaginary, then this is an equality. If g and f are multiples of each other, then the inner product becomes just modulus of c squared times the inner product of f times the inner product of g squared. And the modulus squared of f and modulus squared of g, because they're the same thing. This becomes c squared modulus times f squared, and the same thing here. So let's see what the consequences are. That is, if z is purely imaginary and z is equal to the inner product of f and g, then 0 is equal to the real part of inner product of f and g. But the real part of inner product of f and g, given that g is equal to c times f, is just the real part of c times the inner product of f with itself. But that's just the real part of c. So that says that c must be complex. It must be imaginary purely. So let's call c equal to IA. For a real, the minimum uncertainty condition then, when both of these inequalities are equalities, becomes that g of x is equal to I times a, which is real, times f of x. So remember that f and g represent the standard deviations of the expectation values for two operators. Remember, f was a minus expectation value of a applied to psi, and g was b minus the expectation value of b applied to psi. And so sigma sub a squared is equal to f inner product with f. Sigma sub b squared is g inner product with g. And for position momentum, this becomes the following. H bar over I d by dx minus the expectation value of p applied to psi is got to be equal to IA times x minus expectation value of x applied to psi, because as we saw before, g equals IA times f. So this is g, right? This is g, which is the b operator, and this is f, and you multiply times IA to get this equality. Now, if we rearrange this, and we apply the derivative through here, we get the derivative of psi with respect to x is equal to I over h bar times the quantity expectation value of p from here, plus IA times x minus the expectation value of x, all applied to psi. Now, there's no derivatives here. This is just this is, however, is an operator, so it's x. If I pull the IH bar in, I get I times the expectation value of P over H bar minus A over H bar times X minus expectation value of X, all times psi. Well, we can solve this differential equation. It's not hard. It just becomes the following. So when I take the first derivative, I get all this pulled down from psi. That means it must be in an exponential, right? And so I'm going to have two terms to this. One is an exponential with an exponent of minus A over H bar, X minus expectation value of X. There it is, over 2a, right? And then I have a term that, and I have a divided by 2 because I'm going to have to cancel out the 2 that I get when I take the derivative. And then I have this term, which is simply I times the expectation value of P over H bar times X. Because this then is going to give me just, when I take the derivative here, I just get IP over H bar. And the function back again. Here I have to get this quantity in front. So I have to have this quantity squared. Well, this is just a Gaussian. This is just a Gaussian, and this is an additional term, but this is dominated by this Gaussian. And so the minimum certainty implies a Gaussian wave function, because this can be assumed to be an envelope, and this can be just an oscillatory function. So this is an oscillatory function multiplied times a Gaussian envelope. So that means that Gaussian wave functions give you minimum uncertainty. All right. So the final topic here is the energy time uncertainty. You probably have often heard that that position momentum is sort of a complementary to energy time uncertainty. But it's a much more subtle thing because time is not an operator. So a better way of looking at this is to start by measuring how fast the system changes. So if you look at the time rate of change of the expectation value of an operator Q, an observable Q, that's equal to the time rate of change of inner product of psi with Q psi. Okay, that's just the expectation value of Q. Well, I can pull this in, this derivative in, and I get first a term that looks like partial psi with respect to t, inner product with qt, and then I have the other term where I take the derivative of this term, and I get inner product of psi with the inner product of q, the time derivative of q applied to psi, plus the inner product of psi with q times the first time derivative of psi. So you get three terms. So these two terms are the same, right? And so this can be related to the full time-dependent Schrödinger equation, and it's just related to the Hamiltonian. In fact, it's minus 1 over IH bar times the Hamiltonian, or IH bar times the Hamiltonian. So this is IH bar times the Hamiltonian because it's in the right side. This gives me a minus IH bar, 1 over IH bar, times the Hamiltonian because this is in the bra side, which means I have to take the complex conjugate when I pull it out. So I get minus 1 over IH bar, H applied to psi, inner product with Q applied to psi. And then I have 1 over IH bar plus 1 over IH bar psi, inner product with QH bar psi, QH psi. I have this term left over, which is simply the expectation value of the time derivative of the operator Q. Well, since the Hamiltonian is Hermitian, I can bring it over to the right side. And bringing it over to the right side, I paste it onto the left side of Q, and I get, let me bring the I up on top, I get I over H bar, inner product of psi with HQ psi. plus the expectation value of dq dt minus I over h bar psi inner product with q h bar psi. Well, these two make just the expectation value of the commutator of h and q times I over h bar. And this is still the time derivative, expectation value of the time derivative of q. So we now have this inner product of another commutator of the Hamiltonian with the operator q. So generally, q does not explicitly depend on time. So we can ignore this second term. Let's cancel that out. And if q commutes with h, then the expectation value of q is a constant. And so, right, because this is equal to the expectation value of q, the time derivative of the expectation value of q, the expectation value of q is a constant because it commutes with h. And so we have d by dt of the expectation value of q is I over h bar, expectation value of h, of the commutator of h and q, so if a is equal to h and b is equal to q in the generalized uncertainty relationship, we can write that the variance of h times the variance of q is greater than or equal to 1 over 2i times the expectation value of the commutator of h and q, all quantities squared. But this tells you exactly what that's equal to. We can replace the expectation value of the commutator of h and q with h bar over I times d by dt of q. So we put 1 over 2i, h bar over I, d by expectation value of d by dt of the expectation value of q squared. So this gives us h bar over 2 squared times the time derivative of the expectation value of q, quantity squared. If we take the square root, we have our uncertainty principle between h and q. If they don't commute, then this will be greater than or equal to h bar over 2 times the absolute value of d by dt of the expectation value of q. So let's assume that the standard deviation of the Hamiltonian, because the Hamiltonian's expectation value is the energy, is just called delta E. And sigma of q is just the time derivative of the expectation value of q times the time over which we measure it, delta t. This delta, the small increment of time. Well, if I rearrange this expression then, and I take delta E times delta t, you can see that this is going to give us delta E times delta t is greater than or equal to h bar over 2. If I take and substitute in here, I get that this quantity here can be replaced by, delta t can be replaced by multiplying these two, delta E times dq expectation value dt delta t is equal to h bar over 2 times the absolute value of d by dt of expectation value of q. But this term cancels this term, and so we're left, when we put these together, with delta E delta t is greater than or equal to h bar over 2. So what this means is that delta t represents the time it takes for the expectation value of q to change by 1 standard deviation. Delta t depends on the observable q that you're considering. So if delta E is small, right, if the variance of the energy is small, or the standard deviation of the energy is small, then this must be large. that means that in order for the expectation value of Q to vary by 1 standard deviation, it takes a long time. If, on the other hand, delta E is large, then that means that Q varies very rapidly with time.